Alright guys, so we're ready for the last section in the class, section 9.4. So the new thing that we're doing is hypothesis testing for mean, right? So we've already looked at how to do an hypothesis test, but this is specifically for a population mean, where before we did it for population proportions, right? So there's some similarities between the two, but we remember we have to modify our process a little bit when dealing with population means. Right? So remember, population means the sample of them, they follow the t-distribution, right? So we still have our general 4 steps of hypothesis testing. The first thing is we want to hypothesize. So we want to state your hypothesis about the population parameter, right? So remember, it's always about the population parameter, right? So here, my hypothesis is going to have to do with mu, right? The population mean. Right? So parameter deals with populations, right? And then we need to prepare, right? So we need to choose a significant level and a test statistic and check conditions and assumptions, right? So we're going to review the conditions and assumptions that we need. Significant level, remember, is alpha, right? So the standard significance level is 0.05, right? That's the most widely used. Some others that are widely used is 0.01 and 0.1, right? So those are the most common to use. If a confidence, if a significance level isn't mentioned, usually 0.05 is safe to use, right? That's the standard. Then we need to compute to compare, right? So we need to find my test statistic. So in this case, we need to find t, right? My t critical value, my test statistic, and we need to calculate my p-value, right? Which, remember, the p-value is the area under the curve, right? So if we're doing a right-tailed test, here's t, then this would be p, right? If we're doing a right-tailed test, right? And we'll go over those in a minute, right? And then we need to interpret. Do we reject the null hypothesis or not? And then what does this tell us, right? What does this mean? All right. So hypothesis test. So make a claim about a population mean, right? So my test statistic for one sample t-test are the following, right? So we use this test statistic t. So we're taking x bar, so that's my sample mean, minus mu sub 0, right? So mu sub 0 is what we're testing the population mean to be, and then we divide by the standard error, right? And often enough, remember that sigma is unknown, right? Is unknown. So that's the population standard deviation. So we're going to divide by the standard error estimate, right? So we estimate the standard error by doing this, right? We take the sample standard deviation divided by the square root of n. And remember, I have a degrees of freedom of n minus 1 here, right? And then I listed here 2 conditions that we have to check, right? So we need to check, make sure that we have random independent sample, right? And then we also need to make sure we have a large sample. So that can be satisfied one of 2 ways. We can know that the population is normal, right? Or, it might say approximately normal. That's okay. And then if normality doesn't seem to be an assumption we can make, then my sample size must be at least 25, right? And in practice, the larger the sample size of this, the better, right? So here's an example, which is a nursing example. So in 2010, the mean years of experience among a nursing staff was 14.3 years. A nurse manager took a random survey of a random sample of 35 nurses at the hospital and found the sample mean of 18.37 years with a standard deviation of 11.12 years. Do we have evidence that the mean years of experience among the nursing staff of the hospital has increased? Use a significance level of 0.05, right? So, there should be a lot of things jumping out to you as we're reading this, right? So this year, 2010, really doesn't make a difference for us in the hypothesis testing, but we could include that in the interpretation, right, to make it stronger. But for us, that value doesn't really make a difference, right? So the mean years of experience among a nursing staff was 14.3 years, right? So that's my mu sub 0, right? That's what we're claiming the mean years of experience to be, 14.3 years. We take a random sample of 35 nurses, right? So n equals 35. Sample mean, so x bar is 18.37. And we have a standard deviation of my sample of 11.12. So do we have evidence that the mean years of experience has increased, right? So increased is going to tell me that I want to know, so here's my null hypothesis, right? So my alternate hypothesis has an increase. In other words, so is mu sub 0, is it bigger than 14.3? So remember, this is a right tail test. Right tail test. So the general idea here, if I draw my curve, some t-value is going to exist here, right? And we're going to calculate this. Since we're testing if the mean is greater than 14.3, well, this is a right tail test, right? So we're testing what's the probability of this, right? This area. So we need to find this value, right? This p-value. And if this is bigger than alpha, then we fail to reject, right? But if this p-value is less than alpha, then we have statistical significance and we reject the null, right? And we're told here that alpha, we're using 0.05, right? So here's the general idea that we need. So if we go on the next slide, I have these items more calculated, right? So my hypothesis test, right? Or my null hypothesis is mu equals 14.3, right? So which we have above. And my alternate hypothesis is mu is greater than 14.3. So we need to prepare, right? So do we have a random independent sample? So we're told it's a random sample, and there's nothing that makes us think that we have violated independence, right? So we met those assumptions. And then we need to make sure my sample size is large. Well, n is 35, right? So with n being 35, that's bigger than 25. So my sample size is large enough, right, to satisfy this. So then now I can go ahead and calculate my t-value, right? So I calculate my standard estimate to be about 1.88, which gives me a t-value of 2.16 roughly, right? So we're asked to use technology to find the p-value that corresponds with t equals 2.16 degrees of freedom of 34, right? So if I pull my graphing calculator right up, we would go to second distributions. We want a t-CDF, right? So again, when we're working through this, it's best to draw my picture, right? So what we have here, here's my curve. Here's my t-value of 2.16. This is greater than, so we're doing a right-tailed test, so I need to find the p-value for here, right? So my lower value is 2.16, right? 2.16. My upper value is infinity, right? So 1e99 is how we code that. My degrees of freedom, right? Remember, degrees of freedom is equal to n minus 1. So 35 minus 1 is 34. So we're good there, right? So 34, input in this, and then we hit paste, hit enter, and we can get that p-value. So this p-value, right, the area under this curve is 0.019, right, if we round, right? So if we go to the next slide, I found this using StatCrunch, right? So here's a StatCrunch printout, very similar, right? So we get about 0.019, right? And this is less than my significant level, right? So my p-value is less than alpha, so we would reject the null, right? So this is how we could interpret it. We could say that evidence suggests that the mean experience among the nursing staff has increased, right? And remember, notice we said it hasn't been proved that, or we accept that, right? We're saying that evidence suggests, right? Our statistical evidence suggests that this has increased, right? We don't know for sure if it happened, right? But it seems to be that that's likely, right? Because the opposite seems unlikely, right? That it hasn't increased. So remember here, here's my one and two-sided alternate hypothesis, right? So remember for a two-sided test, right? So for a two-sided hypothesis test, oops, it's not a very good curve here. Let me redraw this a little bit. Right, so remember the idea with a two-sided test, that's if we're trying to test if the mean is different from, right? Here, we're going to find a t-value, right? But we need the area to the right and to the left, right? So both of these areas. So since it's symmetrical, t and negative t, these areas are going to be the same, right? This area equals this area over here, right? So we have to double, right? So if you look up, if you're finding this area, right, then to find the p-value you have to take times 2, right? But if you're plugging things in to your calculator, if you're not using like a t-CDF, you're actually doing a t-test, then that will do it for you, right? So if you're selecting if the mean is not equal to, greater than, or excuse me, less than or greater than, if you're inputting that, and I'll show you how to do that in a moment, then we don't have to do anything with it. The calculator does that for you, right? But if you're using a t-CDF, which I do want you to be able to do both ways for the exam, you would have to double, right? So it's important to understand what's going on and what the calculator is telling us, right? Also, if you use a table, right, that's going to give you the area to the left, right? Typically in most stats tables, right? So both the test statistic and my p-value can be computed using technology. So this is how you can do it with StatCrunch, but we're going to use the graphing calculator, right? This slide. So in order to do this, you will go to second, or excuse me, not second. We just hit the stat menu and then go over to test, and we click t-test option, right? So if I go up, we can input this information, right? So we're going to base this off statistics, right? Some stats we're inputting. So we go down, my mu naught, right, was 14.3. My sample mean, let me see, this was given above, right? My sample mean, we set 18.37. My standard deviation, 11.12. And n was 35. Right? And in this case, we were saying if it's increased, so we need this option selected, right? So then I can go down to calculate, hit enter, and hang on a minute. I notice my standard deviation is 1.12. I made an error. Let me go back into that menu. T-test. So 14.3, 18.37. This should be 11.12, right? You might have been yelling at me, right, as I was going to the next screen. So 35. There. Now we should be good, right? So I was noticing that those values didn't seem quite right, right? So double checking what I entered. Hit enter, and now we're getting a similar p-value, right? So my test statistic 2.16, which we got, right? And then my p-value of 0.019, right? And these were rounded values, right? So inputting all of these into the TI is a little more accurate. So we were able to find that, right? And notice I didn't need to double this at all, right? Because this, so if I go back into the stat menu and go to test, t-test, right? here where I'm selecting if it's not equal to, less than, or greater than, that's why my calculator needs that, right? Because it's going to do that for me, calculate the right p-value. So if I go over to draw, hit enter, it will draw the curve for me, right? And it will also shade the area, right? So right there is my shaded area for my right tail test, right? The area is shaded. It tells me my p-value and my t-statistic, right? So it's pretty nice. Right, so with a two-sided test, what we are getting at is we have double the area, right? And also remember a left-sided test, right, is looking for this area, and for a right-sided test, you're looking for this area, right? So that's why they're called left-sided and right-sided tests, right? So we looked at that. We looked at technology. So I have another example here. So in 2010 season, average home attendance for the NHL hockey games was 17,072. Suppose a sports statistician took a random sample of 30 home hockey games during the 2014 season and found a sample mean of 18,104 with a standard deviation of 1,203.5. Can we conclude that the mean attendance at NHL games has changed since the 2010 season? Right, so the keyword here has changed, right? So immediately you should be thinking that my alternate hypothesis, right, is mu not equal to, right? And my alternate hypothesis is mu equal to whatever we let mu sub 0 be equal to, right? So that would be this 17,072, right? So 17,072 would go here, and 17,072 would go here, right? That's my alternate null, right? So we want to pick out those keywords. Right, so here's my my null hypothesis, and here's my alternate hypothesis. Don't forget we gotta check our conditions. So it is a random independent sample, and my sample size is large enough, right? And we can assume that the population is large, right? So using technology, we can find this a test statistic and p-value, right? So here is the printout from StatCrunch, right? So you should be able to recognize the printout. Right, so here's my degrees of freedom, here's my t-statistic, there's my p-value, right? So those are the things that we want to pay attention to, right? So my p-value is really small, right? So this is less than alpha of 0.05, right? I believe that's what we were using, right? So we were not given an alpha value, right? So remember, we weren't given an alpha value here, so just assume if it's not given, use 0.05, right? So alpha not given, use 0.05. Right? So since the p-value is less than our significance level, we're going to reject null, right? So this is what we can conclude, right? We can say, yes, mean attendance at hockey games has changed since 2010, right? So our statistical evidence suggests this to be true. All right. So now I have two more examples I wanted to work through with you, give you some more practice. So this first one, we have Homestead Lake, Oregon, has an Atlantic salmon catch and release program that has been very successful. So the average fisherman's catch has a mean of 8.8 Atlantic salmon per day. So suppose that we have a new quota system that restricts the number of fishermen has been put into effect for this season. So we're given a random sample that gives us catch per day, and from that, right, we can calculate the sample mean, the sample standard deviation, and we're assuming that we have an approximately normal distribution. So we're told to use a 5% level of significance to test the claim that the population average per day is now different from 8.8, right? So remember, we want to check our conditions, right? So condition 1, right, we want to make sure we have a random independent sample. So that seems to be met, right? Random independent sample. The second condition we need to check is make sure we have a large sample size. Right? So we're told that we have approximately normal distribution. So that's what satisfies here, right? This is okay because we have an approximately large normal distribution. My n value is actually, I believe, 14, right? 14. So that's a small sample, but since we have an approximately normal distribution, we're good, right? So we check my conditions, right? Remember, a third thing that we should check from the essential limit theorem is that we have a large population, right? So remember, the idea is we want to make sure that 10 times n at least exists in the population if we have without replacement. And it's reasonable to assume that we have 140 salmon, right, in this lake, right? Or I think this is a city, so in the Atlantic Ocean, right? It's very, very safe to assume that this is true, right? And I know before I mentioned there was only 2 conditions, right? So if we go way up, on this slide 3, I mentioned that there are 2 conditions, and this is consistent with the book, is what they have listed, but we should also check the large population, right? So I would also recommend checking that, right? So maybe add here, right, that we have a large population. We need at least 10 times n in the population. If without replacement, right? So that was one of the conditions for the essential limit theorem for means, right? So the book says we need these 2 conditions, but I would argue that we should check this guy also, right? All right. So it's going back to our example. So we checked all of those. Let me pull this down. So we'll do this problem in a moment. Give me some more room, right? All right. So we check the conditions, right? So that's good. Then I would go ahead and start state my null, right? State my alternative hypothesis. So my null hypothesis would be, is the population mean equal to 8.8, right? And the alternate hypothesis, remember, this is the same setup. We just need to know what sign to put in here, right? And we're told is different from, right? So that means different from means not equal, right? So we put in not equal. So this is a 2-tail test, right? So if we just note here, we have an n of 14, x bar of 7.36, standard deviation of 4.03. My alpha value is 0.05. So we need to calculate my t statistic, which would be 7.36 minus 8.8, all divided by, so my standard error estimate, which is S, so 4.03 divided by the square root of 14, right? So I'll let you do that calculation on your own, but this comes out to be about negative 1.34, right? So here's my t statistic. So the picture you should be drawing and thinking about is, here's my curve, Here's negative 1.34. Over here is 1.34, right? So I can find the area of this guy. Maybe let that be A. So I need both of these, right? This area would also be equal to A. So my p-value is going to be equal to 2A, right? So I need to figure out what this A guy is, right? So I can do that with my graphing calculator, right? So we can go in and say second distribution. We want normal. Wait, no. We want T CDF, right? A T distribution CDF. So now I need to enter the lower. So the lower would be in negative infinity, right? If I want to find this guy, right? So this would be -1, and then alpha. Wait, no, not alpha. We will hit second, right? Second, and the this guy to get the E, and then 9, and then my upper is negative 1.34. Degrees of freedom, right? We didn't calculate that yet. So degrees of freedom equals n minus 1. My n is 14, right? 14. So 13. Enter that in. Then we can hit enter, and here's A. So A is 0.1016, right? So that's also this area here. So I need to double that to find that, right? So if I do times 2, we can find the p-value to be 0.2032, right? Roughly. So then, remember, alpha is 0.05, right? So my alpha is less than my p-value of 0.2032. So we failed to eject, right? Right, so we need to state, now we need to state a conclusion statement, right? So you can word these different ways, and remember I gave you some things to be cautious of not to say, right? Some things that people typically want to say here but isn't correct to say. So I would say something like this, right? We fail to reject, let me make this larger. So we fail to reject the null hypothesis that the true population mean, I got a typo, let me make this wider. The true population mean for the average, fisherman's catch is 8.8 Atlantic salmon per day. Right? So in other words, there is no statistical evidence to claim that the mean is different from 8.8 Atlantic salmon per day, right? And this is a special type of fish, so I guess this should be capitalized, right? The salmon. Right? So there's my conclusion, right? So you could say something like that, and I've tried to word this in different ways to expose you to different ways you can write this, right? All right. So there was an example of a two-sided hypothesis test, right, for the mean, and I have another example here, which is a one-sided, right, as we're going to see. So according to a student by the Centers for Disease Control, the national mean hospital stay after childbirth is 2.0 days. Reviewing records at our own hospital, a hospital administrator calculates that the mean hospital stay for a sample of 81 women after childbirth is 2.2 days with a standard deviation of 1.2 days. Assuming that the patient represents a random sample of the population, test the claim that the hospital keeps new mothers longer than the national average. Right? So we need to identify some things, right? So first, I mean, before I do anything, I know it's kind of a little out of order of the book. First thing I like to do is check my conditions, right? So the first condition, right? Do we have it? Independent random sample, right? And we're told. So we're saying assume that it represents a random sample, right, of the population. So we met random, and there's nothing here to believe we violate independence, right? So excuse me. So we have an independent random sample. Seems to be met, right? Second step, do we have a large sample size? Well, n is 81, which is definitely bigger than 25, right? So we're good. Then the third thing that I'm suggesting that we check, right, along with the central limit theorem, right, so it follows that, is that we have a large population. So if we take 10 times my sample, we get 810. I think it's safe to say that we have at least 810 women that have had a baby at this hospital, right? So those are all met, right? So now we need to identify some other things. So let's see, my mu that I'm testing, we want that to be equal to 8.8, right? We have an n. Wait, no, that's from the other problem. Sorry about that, right? If I scroll up, I think it's what, 2.0. Yeah, 2.0, right? So this should be 2.0. Let's see, I have an n value of 81. My sample mean was 2.2. My standard deviation of the sample was 1.2. My null hypothesis is that my true population mean is equal to 2.0, right? That's what we're assuming to be true, and we want it to be, see if it's longer than, right? So mu would be greater than 2.0, right? Let's see. So then we need to calculate my t-statistic. So remember, that's x bar minus mu sub 0 divided by s divided by square root of n, right? So if we plug these values in, you should get a t-value of 1.5, right? And that's not rounded. I believe that's exact, right? So here's the picture we need to draw. Here's my curve. Here's 1.5. We're doing a right tail test, right? This tells me right tail. So I'm calculating the area of this right tail. Right? I want to know this. That's my p-value. That area. So I can calculate this in my calculator. Right? So if I go to second distribution, we want t-CDF. My lower value is 1.5. My upper is positive affinity, so 1, and then the E99, right? Degrees of freedom, we didn't calculate that yet, right? N minus 1. So N was 81, so this would be 80, right? So 80, and I hit enter, and I get a p-value equals 0.0688, right? That's what we get. And we can double check this, right? So remember, on the exam, I want you to show all these steps, right? I want you to draw the curve. I want you to calculate the p-value, right, using the t-CDF and for means. But then we can test ourselves. If you go on the stat menu and go to test, and then go to a t-test, then we can double check our work, right? So this would be 2.0 2.2 for X bar. Standard deviation is 1.2. N is 81. And we want to test right tail, right? Is it bigger? So I can go to calculate and get that value, right? So there's my p-value. I get the same p-value, get the same t-statistic, right? And if I also want to, I can go back into my t-test menu, and instead of going to calculate, go down to draw, and it'll draw that for me as well, right? So there's my area, there's my p-value, there's my t-value, right? Let's see, so an alpha was not mentioned, right? So remember what I told you. If it's not mentioned, we assume alpha is 0.05, right? So alpha is less than my p-value, right? So my p-value is bigger than alpha, so we failed to eject, right? So we failed to reject the null hypothesis, right? So now we need to state a conclusion. Right, so we could say that there is not enough statistical evidence for us to believe that the mean hospital stay after childbirth is longer than the national average of 2.0 days for our hospital, right? So we could say something like that, right? We don't have enough statistical evidence for us to believe that our mean hospital stay after childbirth is longer than the national average of 2.0 days for our hospital, right? So there's a conclusion, right? All right, so that should give you enough practice to get through the homework. You know, the general idea is the same as before, right? So here we're just using the t-distribution, right? So don't forget to check my conditions, know how to use the calculator, know how to do it by hand, and so forth, right? All right. So that's the end of the class.